All right, so I decided to break up this next video into two ones. This is just going to be a short video on getting more of an intuitive understanding of that binomial coefficient, and then we'll talk about confidence intervals in the next video. So we've already seen the binomial coefficient in the first video, 7a. Remember, it counts how many times distinct sets of k items that you can choose out of a set of n items. So it's denoted n choose k like that. And remember, that expands to n factorial over n minus k factorial times k factorial. And we talked in the last video about how you can express this n factorial, usually one of these terms in the denominator. In this case, I've chosen n minus k factorial. That'll show up in the expansion of n factorial. And so what you end up with is this shortened form of doing the calculations where you start at n and you multiply that times n minus 1 all the way down to n minus k plus 1. So there's k terms total in the numerator. They start at n, so they're k factors, not terms, excuse me. They go from n all the way down to n minus 1 plus k. Excuse me, I'm sorry, that's wrong. N minus k plus 1 is the lowest one. And then there are k factors in the denominator, and they start at k and go down to 1. And so that's how often we end up calculating these things. So the example we walked through last time was 4 choose 2. 4 factorial expands to 4 times 3 times 2 factorial. And in the denominator, we had 2 factorial times 4 minus 2, which is 2 factorial again. So we lose one of those 2 factorials, and we end up just having to do 4 times 3, which is 12, over 2 factorial, which is 2. And so that gave us our answer 6. So why does this make sense that this is the correct way to count this? And it's actually, I think, a fairly intuitive thing if you think about the process of sampling here. So if we think about choosing 2 items from a set of 4, here's a set of 4 unique items, we want to know how many ordered lists we can compose out of those. Well, the first item to go on the list, there are 4 choices. Okay, we can choose 1 or 2 or 3 or 4. And now for the second item, for each of those options, each of those 4 options that we had, each one has got 3 possibilities. So if we want to add another item to this ordered list that started with 1, we've already used 1 out of our original set. We can't repeat that. We can grab 2 or 3 or 4. So now that's why it's dropped from 4 choices down to 3. And this set of lists here, it started with 2. We can think about adding 1 next, or 3 next, or 4 next, but not 2 because we've already chosen it. So if we think about doing 2 choices into ordered lists, there turn out to be 1, 2, 3, 4, 5, 6, 7. We can continue counting, but it's 4 times 3. So there's going to be 12 ordered lists that we can produce here. So that's the numerator. There were 4 choices at the first level, 3 choices at the second level for every one of the first level choices. So that's why it's a multiplication. 4 times 3 is 12. So that's the numerator. Why isn't that the answer to the question? Well, those are ordered lists. Each set of 2 elements can be put into 2 different ordered lists. So we've double counted each of the sets. Remember, we're trying to figure out how many sets that we can pull out. How many sets of 2 items can we choose out of a set of 4 items, not how many ordered lists. So we've double counted the list, so that's why we have to divide by 2, because we're off by a factor of 2. How can we see that we've double counted? If we just look at all the ordered lists that we chose, here are those 12 that I had on the previous slide, just arranged in a circle. Here's 1 and 2, but here's 2 and 1. Both of those, they're connected by a line because they are the same set, which is 1, 2, curly brace. A set doesn't have an order, so the set 2, 1 is the same thing as the set 1, 2. So we want to know how many sets there are, so we need to avoid this double counting. So we see that each one of these, there are 2 ways of putting it, 1 and 3 or 3 and 1. Each ordered list, we can just swap it around in 2 ways, and that's why we divided by 2. So that made sense how we got the numerator, hopefully, and the denominator. We could see that it was written in 2 ways. That's why we divided by 2, because we've overcounted by a factor of 2. All right, so that's sort of the rationale behind this. I feel like this really tiny example of 4 choose 2 doesn't really demonstrate the denominator super clearly. So let's just walk through a slightly different example. We didn't really demonstrate the formula for why the denominator is a factorial. It was just sort of obvious that there were 2 orders for 2 elements in the list. But let's consider driving 4 elements from a set of 100 choices. So 100 choose 4. So that's the full expression, 100 factorial over 4 factorial times 96 factorial, 100 minus 4. And so there's a lot of crossing out here, and so we end up with, if we think about ordered lists, there's 100 choices for the first step, then 99, then 98, then 97. So those are good. That's the numerator. It's this huge numerator, 94 million, over 94 million. And the denominator is going to be k factorial. That's going to be the part that goes in the denominator after we've crossed out the other factor. So 4 times 3 times 2 times 1, since we're choosing 4 items. So why is it k factorial? Well, it's actually really similar to what we were thinking about before. We have, let's just say, one of our collections of 4 elements. I'll just, for simplicity, use the first 4 elements on the number line, 1, 2, 3, and 4. How many different ordered lists can we write those in? It's complete all 4 of them now, right? So like how much overcounting was done when we counted, remember the numerator, this 94 million, that was sort of all the ordered lists. How much do we overcount? Well, there's 4 options again for the first step. And there's 4 options for the first step, and remember we could add 3 for the next one, so 4 times 3. But now when we get here we've already used 1 and 2, so there's only 2 other options that can go as the next item here, right? So for each of these lists that already have 2 elements, there's only going to be 2 items that we can add. So it's 4 times 3 times 2, right? So this one had 1 and 2, but it didn't have 3 and 4, so we could add 3 as the next one, or 4. But we can't add 2 or 1 again, so there's only 2 choices. And the same thing applies anywhere here. Like this list here has 3 and 4 already, so we can add 1 to it, or we can add 2 to it. But there's 2 choices in every case. And then we still don't have a full list. We have lists of 3, but now each of these lists of 3, there's only 1 missing item, so there's not really a choice anymore. So it's 4 at the first step times 3 at the next step times 2 at the next step times 1. Right? So 4 choices at the first level times 3 choices times 2 choices times 1 choice. And, each time it's like 4 choices at the first level and 3 choices at the second level. Those apply to each of the first level choices. And the 2 choices at the third level, those apply to every second level choice. So that's why it's accumulating and multiplying times itself. So that gives us this factor of how much things have been overcounted. So basically our original list was 24 times too big because our method for starting at n and going k steps down, decreasing by 1 each time, and multiplying those together, those gives us the number of ordered lists correctly, but it's 24 times bigger than the number of sets. And so that's why we have the 24 in the denominator, and hopefully that'll make it a little bit easier to remember this compact form of the binomial coefficient that we see a lot. Technically the way I've written it, this only applies for larger numbers of n and k and n minus k, but in general similar crossing out happens all the time. And there are a few other ones that might be useful to you just to think about the specific formula, how they simplify. So if n choose 0, well, k factorial on the bottom is 1, and then n minus 0 is still going to be n, so it's going to be n factorial over n factorial. And so that's always 1. So whenever you see anything choose 0, it's going to be 1. Anything choose 1, that's n factorial over 1 factorial and n minus 1 factorial. Most of those terms are going to cross out, and you're going to end up with just an n left in the numerator. So n choose 1 is always n, and n choose 2 is always going to be n times n minus 1 over 2. So you don't need to worry, 2 factorial is just 2. And so this is often easier, like if you're doing 100 choose 2, you can think of it as 100 times 99 over 2, and that's helpful because one of these is going to be an even number, so we can just think of this as like, well, this just all reduces to 50 times 99. You can always use the full formula, but this video hopefully will give you a sense of where the numbers are coming from and some quick tricks for some of these commonly occurring combinations. So I hope that helps. Next video, we're going to talk some about confidence intervals.